What if the most important discovery in human history was never something humanity actively searched for, but something that had been quietly waiting for us to notice it? Imagine a silent observer positioned somewhere in the deep architecture of space, not drifting randomly, but patiently watching, programmed to awaken only when a specific biological or technological signal finally appeared within its range. For decades, that idea belonged almost entirely to science fiction, the type of concept explored in speculative books and theoretical discussions. Yet today, something has appeared in the data that is forcing scientists to examine that possibility with surprising seriousness. Astronomers are now analyzing the strange telemetry of an interstellar object whose motion refuses to follow the predictable rules that normally govern celestial mechanics. The object is known as 3I Atlas, and the measurements associated with its trajectory suggest something unusual. Instead of simply passing through our solar system like other wandering bodies, it may have been positioned in a way that allowed our system to encounter it. To understand why researchers are paying attention to this anomaly, we first need to look at the invisible framework that controls the movement of objects throughout the galaxy. Every comet, asteroid, and interstellar traveler moves according to the gravitational dynamics of stars, planets, and the overall motion of the Milky Way. Astronomers often measure an object's speed relative to something called the local standard of rest, which represents the average motion of stars in our part of the galaxy. When scientists calculated the velocity of 3I Atlas using that reference frame, the result immediately raised eyebrows. Most interstellar visitors enter our solar system at incredible speeds, often between 26 and 32 kilometers per second. Those velocities reflect violent gravitational encounters that occur as objects are flung away from distant planetary systems. Famous examples include the mysterious interstellar visitor known as Oumuamua and the comet Borisov, both of which crossed our solar system at remarkable speeds before continuing their journeys into deep space. But 3I Atlas behaved very differently. Instead of racing through the system like a cosmic projectile, it was moving at less than 5 kilometers per second relative to the galactic background. In the enormous scale of the Milky Way, that speed is astonishingly slow, almost as if the object had been lingering in place while stars gradually moved around it. This strange detail is what has led some researchers to revisit an old theoretical concept known as the sentinel hypothesis. The idea was first proposed in 1960 by mathematician Ronald Bracewell, who suggested that an advanced civilization might explore the galaxy not by sending enormous spacecraft to every star, but by deploying autonomous probes to strategic gravitational locations. Those probes could remain dormant for extremely long periods, waiting until a developing civilization entered their observational range. In that scenario, stars themselves become the moving pieces of the puzzle. Our own solar system travels around the center of the Milky Way at a staggering speed of about 220 kilometers per second. Over millions of years, that motion slowly carries our planetary neighborhood through different regions of interstellar space. If a probe had been placed somewhere along that path, the solar system could eventually drift directly into its observation zone. That raises an obvious question. How would such a device detect us long before our spacecraft ever reached it? The answer lies in the electromagnetic signals that humanity has been releasing into space for more than a century. Radio broadcasts, radar pulses, and television transmissions have expanded outward from Earth at the speed of light, forming what scientists call a growing radiosphere around our planet. Any sufficiently sensitive instrument positioned within several dozen light-years could theoretically detect those signals and identify them as artificial. Advanced sensors might also search for atmospheric clues such as oxygen and methane existing together in chemical imbalance, or even traces of industrial pollutants that suggest technological activity. For nearly 100 years, our planet has effectively been announcing its presence to the galaxy without intending to. According to theoretical models, a probe located within 50 light-years might already have recognized those signals decades ago. And when scientists began reconstructing the trajectory of 3I Atlas, they noticed something intriguing about the direction from which it entered the solar system. Instead of arriving along a random path, the object approached from above the plane of the planets, traveling from the direction of the constellation Ursa Major. That route provided a remarkably clear line of sight toward Earth for several weeks before the object reached the closest point in its orbit around the Sunday. For a natural asteroid or comet, that alignment could simply be coincidence. But when all of these details are examined together, the pattern begins to look less random. A slow velocity relative to the galaxy, a trajectory that offered a direct observational window toward Earth, and the timing of its arrival during the modern technological era all combine to form a puzzle that scientists are still trying to interpret. The data alone does not prove anything extraordinary, but it raises a question that researchers cannot easily ignore. If the sentinel hypothesis were ever correct, the arrival of an object like this might look exactly the way this one does. And that possibility is precisely why astronomers are now examining every detail of 3I Atlas with such careful attention, because the next pieces of evidence hidden inside the telemetry may reveal whether this object is simply another interstellar wanderer or something far more deliberate in its design. If you want to see where the evidence leads next and uncover the deeper mysteries behind this strange traveler, make sure to stay with the story until the end. Now the real mystery begins when scientists started looking beyond the object's path and focused on the tiny details hidden inside its motion. In space, every object tells a story through the way it moves. Gravity, sunlight, and internal composition all leave fingerprints on an asteroid or comet's trajectory. For natural objects, those patterns are usually messy and unpredictable. Ice melts unevenly, gas vents burst from random cracks, and the object begins to wobble or tumble in response. But when researchers began examining the motion of 3I Atlas more carefully, the numbers revealed something far less chaotic. Instead of drifting like a typical comet being pushed by sunlight, the object showed signs of a very specific type of movement known as non-gravitational acceleration. At first glance, this might not sound unusual. Many comets experience small pushes when gases escape from their surfaces as they warm near the Sunday. But the pattern recorded for this object contained a feature that immediately caught the attention of orbital analysts. The official database, maintained by NASA's Jet Propulsion Laboratory, initially described the motion as a simple radial push, meaning the force appeared to push the object directly away from the Sun as expected. That explanation fits the behavior of ordinary comets. However, when independent researchers began re-examining the data using more detailed modeling techniques, they discovered something that didn't quite match that simple explanation. Along with the outward push, there appeared to be another force acting sideways along the object's path. This tangential acceleration was nearly as strong as the outward one, creating a subtle but measurable shift in its trajectory. In the physics of natural comet activity, such balanced sideways movement is extremely rare. Normally, gas escaping from an uneven surface produces irregular thrust in different directions, causing the object to spin erratically. Yet the data from 3I Atlas hinted at something far more organized. The search for clues then moved to the most powerful observing instruments available. Astronomers turned to high-resolution images captured by the Hubble Space Telescope and processed them carefully to remove the bright circular glare surrounding the nucleus of the object. What appeared after that filtering step surprised many researchers. Instead of a chaotic cloud of gas jets emerging from random spots, The imagery revealed three distinct streams of material emerging from the object's surface. Even more striking was their placement. The jets appeared to be spaced almost perfectly around the equator of the object, separated by roughly 120 degrees from each other. In simple geometric terms, they formed a triangular arrangement around the rotating body. That kind of symmetry is extremely uncommon in natural comet structures, where cracks and vents normally appear in irregular patterns shaped by impacts and thermal stress. Scientists then ran simulations to see what such a configuration would do to the motion of the object. The results were fascinating. If three jets were positioned exactly 120 degrees apart and released gas in a coordinated pattern, the forces they produced could balance one another while still generating a steady sideways thrust. In other words, the object could maintain stability while adjusting its trajectory at the same time. Instead of tumbling randomly through space, it could move with a controlled sideways push that gradually altered its path. This explanation would neatly account for the tangential acceleration seen in the orbital data. Another clue emerged when astronomers examined how quickly the object was spinning. Most interstellar bodies rotate unpredictably because sunlight slowly twists them through a process known as radiation torque. Over time, this can produce chaotic tumbling that constantly changes the orientation of the object. But observations of 3I Atlas showed something much more stable. Its rotation period appeared to be extremely consistent, repeating every 7.1 hours with almost no variation. That kind of regular rhythm suggests the object is maintaining a carefully balanced distribution of mass while spinning. In orbital mechanics, this condition is known as spin stabilization. Engineers often design spacecraft to rotate in exactly this way because it naturally spreads mass evenly and helps maintain structural stability. When all of these pieces are placed together, the picture becomes more intriguing. A stable rotational heartbeat, symmetrical jet placement, and measurable sideways thrust combine to create a motion profile that looks surprisingly organized. None of these observations alone prove that the object is artificial. Nature is capable of producing remarkable structures under the right conditions. Yet the level of symmetry and control implied by the data has encouraged some scientists to keep an open mind about more unusual explanations. As researchers continue examining the telemetry, the next stage of the investigation moves beyond simple motion analysis and begins exploring how this object might be interacting with sunlight, plasma, and electromagnetic forces as it travels deeper into the solar system. Because if the unusual patterns seen so far continue to appear in the data, the true purpose of this mysterious traveler may become much harder to explain as a simple wandering rock from another star system. Stay with the investigation, because the next layer of evidence reveals even more details that challenge the idea that 3I Atlas is just another interstellar comet drifting silently through space. As the investigation moved forward, scientists realized that the motion of 3I Atlas could not be understood by studying gravity alone. The object was interacting with sunlight, charged particles, and magnetic fields in ways that suggested something far more complex than simple comet activity. In the physics of light, every photon carries a tiny amount of momentum. When sunlight strikes a surface, it exerts a microscopic pressure known as radiation pressure. For most asteroids and comets, this force is incredibly small and usually has almost no noticeable effect on their motion. But if an object has the right structure or reflective properties, sunlight itself can become a form of propulsion. This concept is already used in experimental spacecraft designs called solar sails, where large reflective surfaces capture the momentum of light to generate thrust without fuel. When astronomers examined images of 3I Atlas taken after it passed its closest point to the Sun, they noticed a rare feature known as an anti-tail. Normally, comet tails stream away from the sun because solar radiation pushes dust and gas outward. An anti-tail behaves differently. It appears to point toward the sun rather than away from it. This phenomenon can occur naturally under specific viewing angles, but in this case, the structure seemed unusually persistent. The feature suggested that material was being directed in a way that allowed sunlight to push against it more efficiently. If the surrounding cloud of particles was reflecting solar photons in a coordinated direction, it could act like a gigantic natural sail interacting with the light of the Sunday. While that possibility alone was fascinating, another set of observations introduced an entirely new piece to the puzzle. Instruments designed to study the composition of the gas surrounding the object detected elements that appeared in unusual concentrations. In particular, measurements hinted at elevated levels of nickel ions in the expanding cloud of particles around the nucleus. Nickel is not unheard of in cometary material, but the quantities suggested by the data seemed far higher than what astronomers normally expect in icy bodies formed in distant planetary systems. If those readings were accurate, the object might be releasing particles produced by high-energy processes rather than simple melting of frozen water or carbon dioxide. This possibility led some researchers to explore what they called the plasma interaction hypothesis. In space physics, plasma is an electrically charged gas that responds strongly to magnetic fields and solar wind. If the material leaving the object contains charged ions moving at high velocity, those particles could interact with the solar wind in ways that generate additional forces. Instead of a simple jet of vapor drifting away from the surface, the outflow could behave more like a stream of energized plasma. That interaction might explain why the sideways acceleration measured in the object's motion appears so stable and consistent over time. Another fascinating detail emerged when scientists compared the chemical signals detected around the object with the background environment of the solar system. The concentration of certain ions seemed significantly higher than the levels normally found in the solar wind. If confirmed, this would suggest that the particles are originating from the object itself rather than from surrounding space. Such an unusual composition could imply that the material inside the nucleus has undergone processes that differ from those shaping ordinary comets. Researchers began running complex simulations to understand what type of internal structure could produce those results. One possibility is that the object contains pockets of material capable of releasing energetic ions when exposed to solar radiation. Under the right conditions, those ions could be accelerated by electromagnetic forces, forming a kind of natural plasma engine. While this idea remains speculative, it would provide a mechanism for the steady thrust that analysts continue to observe in the orbital data. At the same time, scientists studying the object's rotation returned to the consistent 7-1-hour cycle recorded in earlier measurements. This steady rhythm, sometimes described as the object's heartbeat, appears to remain stable even as the object moves closer to the inner solar system. That stability is significant because many natural interstellar objects begin to wobble or break apart when heated by sunlight after traveling for millions of years through the cold vacuum between stars. Yet 3I Atlas appears to be maintaining its structural integrity with remarkable precision. When all of these observations are considered together, they reveal a traveler that behaves very differently from typical comets or asteroids. Its symmetrical jets, stable rotation, unusual particle composition, and consistent sideways thrust create a pattern that continues to challenge simple explanations. None of these features alone prove that the object is artificial or intentionally controlled, but they do suggest that something about its structure or internal processes, is unlike anything astronomers have studied before. As the object continues its journey deeper into the solar system, scientists are now turning their attention to its next predicted destination because the trajectory analysis indicates that 3I Atlas is not simply drifting past the planets. Instead, the calculations suggest it is moving toward a location that could play a critical role in revealing the true nature of this mysterious interstellar visitor. As researchers continued tracking the trajectory of 3I Atlas, one prediction began to dominate the discussion inside orbital analysis groups. The object was not simply crossing the solar system on a random path. Instead, calculations showed that it was heading toward a very specific region, dominated by the most powerful planet in our system. According to the projected orbital models, the object would pass extremely close to the gravitational boundary surrounding Jupiter, an invisible region known as the planet's Hill sphere. This zone marks the distance where Jupiter's gravity begins to dominate over the gravitational pull of the Sun for nearby objects. In practical terms, it acts like a massive gravitational gateway where passing bodies can be captured, redirected, or accelerated. The predicted encounter window falls around March 16, 2026, and what makes the projection so remarkable is the precision of the target. Orbital simulations indicate that 3I Atlas is approaching this region with an accuracy that is difficult to explain through random gravitational interactions alone. The estimated approach falls within roughly 57 kilometers of the calculated trajectory line, a level of accuracy that corresponds to about 1 part in nearly a million. In celestial mechanics, natural objects usually do not display that level of targeting unless they have been guided by very specific gravitational encounters over long periods of time. Yet the path taken by this object does not show the complex chain of planetary slingshots that would normally be required to produce such precision. To understand why the potential meeting with Jupiter is so important, scientists began examining the planet's environment from another perspective. Jupiter is not simply the largest planet in the solar system, it is also one of the most powerful natural electromagnetic generators in the entire planetary neighborhood. The planet possesses a magnetic field roughly 20,000 times stronger than Earth's, creating a massive magnetosphere that extends millions of kilometers into space. Within this region, charged particles are constantly accelerated along magnetic field lines, producing enormous electrical currents that flow between Jupiter and its moons. One of the most intense of these interactions occurs between Jupiter and its volcanic moon Io. As Io orbits the planet, it releases huge amounts of sulfur and other material into space, forming a dense ring of plasma known as the Io torus. This electrically charged environment interacts with Jupiter's magnetic field to generate currents that can reach millions of amperes. The entire system behaves almost like a gigantic cosmic power generator, producing powerful radio emissions that can be detected by instruments even from Earth. Because of this extraordinary environment, some scientists have begun asking an unusual question. If a device or structure were moving through the solar system and needed to transmit a signal across enormous distances, Jupiter could serve as a natural amplifier. Instead of relying entirely on its own limited energy supply, such a system could theoretically interact with the planet's magnetic field and plasma environment to strengthen or modulate a signal. By injecting energy into the electromagnetic pathways that connect Jupiter and Io, it might be possible to influence the planet's natural radio emissions and use them as a broadcast channel capable of traveling across interstellar space. While this idea may sound speculative, the physics behind it is grounded in well-understood principles of magnetospheric science. The real mystery is why 3I Atlas appears to be heading directly toward this powerful planetary system. If the object were simply passing by the Sun, countless other trajectories would have carried it harmlessly away from the inner planets. Yet the orbital models show that its sideways acceleration, the same tangential force observed earlier in the data, is slowly adjusting its path in a way that keeps the approach aligned with Jupiter's gravitational boundary. As the predicted encounter grows closer, scientists are watching the telemetry with increasing attention. Each new measurement provides additional insight into how the object is moving and whether the unusual forces affecting its trajectory remain consistent. If the sideways thrust continues guiding the object toward the Jovian system with the same level of accuracy, it would become increasingly difficult to dismiss the behavior as simple coincidence. For now, researchers remain cautious. Space is filled with phenomena that appear mysterious until better data reveals their natural causes. Yet even the most conservative scientists agree that 3I Atlas is providing one of the most intriguing orbital puzzles seen in recent decades. Whether the explanation ultimately turns out to be an exotic natural process or something far more unexpected, the approaching encounter with Jupiter may soon provide the evidence needed to resolve the mystery. And if the object continues adjusting its course in the same deliberate pattern, the next phase of the investigation could reveal whether this interstellar traveler is merely passing through our neighborhood or deliberately navigating toward a destination that may hold the key to its true purpose. As researchers continued tracking the trajectory of 3I Atlas, one prediction began to dominate the discussion inside orbital analysis groups. The object was not simply crossing the solar system on a random path. Instead, calculations showed that it was heading toward a very specific region dominated by the most powerful planet in our system. According to the projected orbital models, the object would pass extremely close to the gravitational boundary surrounding Jupiter, an invisible region known as the planet's Hill sphere. This zone marks the distance where Jupiter's gravity begins to dominate over the gravitational pull of the Sun for nearby objects. In practical terms, it acts like a massive gravitational gateway where passing bodies can be captured, redirected, or accelerated. The predicted encounter window falls around March 16, 2026, and what makes the projection so remarkable is the precision of the target. Orbital simulations indicate that 3I Atlas is approaching this region with an accuracy that is difficult to explain through random gravitational interactions alone. The estimated approach falls within roughly 57 kilometers of the calculated trajectory line, a level of accuracy that corresponds to about 1 part in nearly a million. In celestial mechanics, natural objects usually do not display that level of targeting unless they have been guided by very specific gravitational encounters over long periods of time. Yet the path taken by this object does not show the complex chain of planetary slingshots that would normally be required to produce such precision. To understand why the potential meeting with Jupiter is so important, scientists began examining the planet's environment from another perspective. Jupiter is not simply the largest planet in the solar system. It is also one of the most powerful natural electromagnetic generators in the entire planetary neighborhood. The planet possesses a magnetic field roughly 20,000 times stronger than Earth's, creating a massive magnetosphere that extends millions of kilometers into space. Within this region, charged particles are constantly accelerated along magnetic field lines, producing enormous electrical currents that flow between Jupiter and its moons.